Good day, everyone. Welcome to EGN 3343. This is thermodynamics, and today we are going to continue our discussions of the properties of a thermodynamic system, and we are going to now shift focus to ideal gases. Now, so far we've been talking about the properties of pure substances, and substances, pure compressible substances, are those that are bound to change phase depending on the conditions. They could go from compressed liquid to saturated liquid, to wet vapor, to saturated vapor, all the way up to superheated vapor. Now we're going to talk about a different class of substances, which we frame or classify within the category of ideal gases. And these are actually quite easier to deal with because they behave much nicer than substances, because within the range of thermodynamic processes that we're going to study, ideal gases do not change phase. So we don't have to deal with this thing of going into a wet vapor zone where two properties are not independent from each other and generating an additional property called quality. Ideal gases do not undergo this process. Now, that doesn't mean that these gases that we are going to classify within ideal gases cannot change phase. They do, but at really high temperatures, or really high pressures or low temperatures, they can actually liquefy. But within the regular thermodynamic processes that we are going to study, they are bound to stay within the same phase. And so is the case for air, for example. Air is a typical example of an abundant ideal gas that is used in many thermodynamic processes. Actually, is the most widely used gas in any thermodynamic process, because any single internal combustion engine deals with air as the system substance, or in this case, a system ideal gas. What goes into the engine of your car is air that is being compressed inside a cylinder. It goes a compression process, then it goes a heat addition process. When you add the fuel, or when the fuel inside is actually ignited, that's a heat addition process. Then it goes another process of expansion, and then it goes through another process of heat release. And then that way you create power. This is actually a power cycle, thermodynamic power cycle. But the thermodynamic system is composed of air, which is considered to be an ideal gas, and it will respond to the properties and behaviors that we are going to derive here in this class today. All right, so what is an ideal gas? It is a fluid far enough from its saturation curve that is not likely to condense into the liquid phase in any process. It's generally referred to as a gas. So if we have, for example, water vapor, but the water vapor is so superheated to the right of the saturation dome that the saturation dome is so far away from it that under regular conditions, under the thermodynamic process in scope or in question, that water vapor will not change phase. It will stay as vapor. So then maybe we can even consider water vapor to be a gas. Okay? Yes, it is. It is a gas when it's really far away from the saturation dome. Now, if the temperature is high enough and the pressure is low enough, then we can consider it to be an ideal gas. It will behave as an ideal gas. And then what is the difference between an ideal gas and just a regular gas? Well, an ideal gas is one that responds to a specific relationship between its fundamental thermodynamic properties. It's a gas that responds to a very specific relationship between pressure, temperature, and volume. Okay? Pressure, temperature, and volume work in harmony in a very simple equation. Okay? Remember when we talked about substances and we said that there are relationships between pressure, temperature, and volume. Those relationships could be algebraic. Those relationships could be tabulated, and those relationships could be graphical. Well, for the case of substances, we rely on tables because the relationships are very difficult because of that change of phase problem. Now, when it comes to ideal gases, that relationship becomes very easy, so we can actually rely on equations, a very simple equation. And we consider an ideal gas when we can rely on that particular equation. So remember, anything that's far away to the right of the saturation dome, very far away into the superheated zone, then we consider a gas. If the temperature is high enough and the pressure is low enough, then we consider it an ideal gas because it will behave very nicely. Now, what is high enough and what is low enough? Well, it means that if the temperature is at least twice the critical temperature, remember that the critical temperature is the temperature at the top of the saturation dome. If we're looking at a temperature that is all the way on the top of that times 2, so a temperature that is twice as the critical temperature of that particular substance. And we're dealing with a pressure that is about 10% or less of the critical pressure, the pressure right at the top of the saturation dome, divided by 10 or less, that means that that gas is far, far, far away from the saturation dome. And on the regular processes, the processes of compression and expansion, as long as we don't do anything really dramatic to the system, it is going to stay as an ideal gas. Then we can consider it to be an ideal gas. That is the definition of far enough. All right. So the key here is, well, ideal gases are substances, but they actually do not change phase. And because they do not change phase, because they're far, far away from the saturation dome, they behave very nicely. And the equations that govern the relationship between these properties, the thermodynamic properties, pressure, temperature, and volume, and then further on the energy and entropy and so on, are very easy to deal with. Very easy because they're algebraic. Very easy because they're just equations. We don't even have to rely on tables. There are tables, but they're not necessary. Okay, so for an ideal gas, this is the situation. The relationship between the three fundamental properties, pressure, volume, and temperature, and notice we're talking about volume in the sense of specific volume, remains constant. P times V divided by temperature remains constant for every ideal gas, whichever it is. Now the ideal gases that we're going to be dealing with in this class are 6. Air is the most abundant and the most widely used in all thermodynamic processes. Otto cycles, gas engines, diesel cycles, dual cycles, Stirling engines, Brayton cycles, and power plants, gas power plants, gas turbines, the turbines of an airplane. Those are all thermodynamic processes that we are going to study here, and they're all composed of air as the system substance. Then we have oxygen, O2, then we have nitrogen, N2, then we have hydrogen, H2, then we have CO2, carbon dioxide, and then we have CO, carbon monoxide. So we have those 6 gases to deal with, and that we can consider ideal gases. Well, that doesn't mean that oxygen, for example, cannot change phase. We know that we can make liquid oxygen. It's used in our space applications to burn the fuel. Now, oxygen can actually change phase, can actually condensate into liquid. We can even solidify it if we wanted to, if we increase the pressure to a very, very, very high pressure. However, normally oxygen is in a region that it will not condensate. In order to condensate it, you need to dramatically affect those properties. You need to actually increase the pressure by factors of 500, and you need to decrease the temperature to very, very low temperatures in the minus 200 degrees Celsius range. Now, this constant of proportionality between PV and T is called the gas constant. Every single gas is a different R. A gas constant R. So if we're talking about air, that R will have a value. If we're talking about hydrogen, that R will have a value. If we're talking about oxygen, it will have a different value. So PV divided by T is equal to a constant called R. Okay. Now that constant R, let's go back to that page. P times the specific volume divided by the temperature of any ideal gas equals to a constant that is called R. R is the gas constant, which is different for every single gas. All right. Now, how do we define that constant, and where do we find it? Obviously, it's tabulated. We can find it in tables, and I've actually provided those tables for you. They're online. But that constant comes from something called the universal gas constant. There is a universal one that applies to every single molecule in the universe. The universal gas constant, Ru, yields the same value for all gases. And then when you divide by the molecular weight of a specific gas, then you get the specific gas constant, the one that goes into the equation of state. This is called the equation of state. All right. So equal number of molecules behave similarly. So there's got to be a universal constant. If you have molecules of hydrogen and molecules of oxygen, we know that they're composed of different amounts of protons and neutrons and so on. But if we can actually count those things, we will know that they proportionally behave the same. Now, this universal gas constant, you can find it on the text or in tables. It's a good number to remember, 8.314 kilojoules per kilomole Kelvin. The universal gas constant in U.S. customary units, 1,545 pound-force feet divided by pound-mole, degree Rankine, or 1.986 BTU divided by pound-mole, degree Rankine. So these are different units in which you can see the universal gas constant. It is a good idea to remember this first one here, so you don't have to be looking it up. 8.314 kilojoules, kilomole, Kelvin. Now, what is a kilomole? And in particular, what is a mole? A mole is not a molecule. Okay, a mole is a fixed number of molecules. Now, a mole is an Avogadro number of molecules. It's a very, very large number of molecules. It's a fixed number. It's a number that's already been set. The Avogadro number is another universal constant that is 6.022 times 10 to the 23. It's a huge number. It's in the trillions, actually quadrillions. It's the number of molecules inside a mole. Okay. M is the molar mass or molecular weight, which equals the mass of a mole of a specific gas. So for example, CO2 has a molecular weight of 44 kilograms per every kilomole. A kilomole is 1,000 of these Avogadro number of molecules. So it's actually 6 times 10 to the 26 molecules. Now, 6 times 10 to the 26, imagine 6 times and 26 zeros on the right, molecules of CO2 weigh 44 kilograms. So you can say 6 times 10 to the 23 molecules of CO2 weigh 44 grams, or 6 times 10 to the 23 kilo, or 6 times 10 to the 26 molecules of CO2 weigh 44 kilograms. That is what the molecular mass is about. And obviously, molecular mass of an element or a molecule is higher depending on the composition. It's higher for a higher composition of the molecule. For example, the oxygen molecule will have a lower molecular weight than CO2 because the CO2 molecule has a carbon atom attached to it, whether the O2 molecule has just oxygen. So the universal gas constant relates to the specific gas constant R as RU divided by the molecular weight. So when you want to know what the gas constant for air is, you divide that universal gas constant, which is 8.314, you divide it by the molecular weight of air. If you want to know what the gas constant is for CO2, for example, you divide RU, 8.314, you divide it by the molecular weight of CO2, 44, and you get exactly 0.189. 0.189 is the gas constant of CO2. Now, what are the units of the gas constant of CO2? Well, notice that the universal gas constant is in kilojoules per kilomole Kelvin. If you divide that by the molecular weight, which is in kilograms per kilomole, you will get kilojoules per kilogram per Kelvin. So which actually means is the amount of caloric content of a kilogram of CO2 to raise the temperature by 1 degree. That's what it means. Okay? So the specific gas constant is equal to the universal gas constant divided by the gas's molecular weight. All right? So if we combine the previous ideals, and then we can generate the different versions of the ideal gas equations of state. These are the so-called equations of state. This is the first equation of state. PV is equal to RT. You can frame that. Or PV over T is equal to R. This is the one that we actually already illustrated. PV is equal to RT. Do not forget that equation. That is the equation that applies to ideal gases. PV equals to RT. Now, if we make the specific volume what it is the total volume divided by the mass, then we yield this new equation. P times the absolute volume is equal to the mass times the gas constant times T. Now we're talking about the specific gas constant, the gas constant. P times total volume is equal to the mass times R times the temperature. That is the mass of the system. So this is another form of the equation of state for ideal gases that includes the mass. When you include the mass, then the volume becomes the total volume. Furthermore, we know that the R is the universal constant divided by the molecular weight. And we know that N, or the number of moles, is the mass of the system divided by the molecular weight. So we can combine these two things into a new class or a new form of the equation of state. Let's say that we are given a system that we don't know the mass, but it turns out that we actually know the number of moles in the system. We know the mole content of the system. We are told that this system has, 10,000 kilomoles of air. If that's the case, then PV, we can relate the pressure, the volume, and the temperature as P times V equals the number of moles in the system times the universal gas constant, that's 8.314 kilojoules per kilomole Kelvin times the temperature. Now this equation here applies to every single gas, ideal gas in the universe. It applies to all as long as you know the number of moles. The constant is exactly the same for all the gases, the universal gas constant. Okay, so remember these two equations. They are going to be very important from now until the end of the semester, and they only apply to ideal gases. You cannot apply this equation that relates pressure, volume, and temperature to substances that change phase. I don't want to see you applying this to water or applying this to any refrigerant, R134 or R22 or ammonia or any of these things for which we have tables online. We only apply these equations to ideal gases. Only to ideal gases. Air, oxygen, nitrogen, hydrogen, CO2, and CO. There are many more gases, many more ideal gases, but we are only going to consider those six. Again, air, nitrogen, oxygen, hydrogen, CO2, and CO. Now notice out of all these gases, the six gases, the only one that is not a uniform homogeneous molecule is air. Air is actually a compound of many gases. Air is composed of oxygen, nitrogen, CO2, water vapor, and many other things. Okay, mostly nitrogen. Air is composed of about 70% nitrogen, and it has some 20% of oxygen and other things. But it's mostly nitrogen and oxygen. Okay, so air is not really a chemical molecule. Air is a compound of other types of molecules. All right, but it's also considered an ideal gas, and it's the most abundant one, and it's the one that we're going to be working with more heavily in thermodynamic processes. Okay. Now let's look at other properties. We've already defined the relationship for ideal gases for pressure, volume, and temperature. We already related those through the state equation. So no longer we use tables to calculate the volume or the temperature or the pressure. If we know the pressure and the temperature, we know the volume. If we know the volume and the pressure, we know the temperature. If we know the temperature and the volume, we know the pressure. All we do is use the equation of state. Now what about other properties? How about internal energy and enthalpy? Okay. Do we have tables? Can we come up with an equation? Well, we can actually do. We can actually do so. And let's recast a little bit of calculus in order to do this. Now remember from calculus, and if you've taken calculus from me, actually problem analysis, or if you took calculus previously, and this is something that we're not going to need. We're just going to use this particular tool for the definitions of the equations that we're going to come up with at the end for energy and enthalpy. We don't need this in order to solve problems. This is just a formulation. In calculus, if you have any function z that depends on two properties, x and y, then you can take the full derivative, the substantial derivative of that quantity z, as the partial of z with respect to x times dx plus the partial of z with respect to y times dy. That's called the chain rule. You can actually take a derivative of a multivariable function. This is a function z that depends on x and y. It's a 3D function. Z that depends on x and y. So like for example, p that depends on t and v, or v that depends on p and t. You can take the state equation and do this. But you can generalize this for any quantity. Why are we saying a function that depends on two variables? Well, remember the state postulate. We defined this a few lectures ago. The state postulate says that for any simple interaction thermodynamic process, you need two properties in order to fully define the state of the thermodynamic system. So for any property you can think of, energy, enthalpy, entropy, anything you can think of, you only need two other properties in order to fully define the system. So let's work with these. Now, using this, we're going to apply this to any thermodynamic property, considering the state postulate. Remember again the state postulate. It means that we can define the state of a thermodynamic system knowing two properties already. If we know two, that means that we theoretically know everything else, as long as we can come up with an equation. So let's start with internal energy, U. We know that U is an important property that we have to define. We know it's in the tables for water and all the other substances. Now let's see if we can come up with a relationship for energy for the ideal gases. Now in the case of ideal gases, let's say that U depends on temperature and volume. We could say that it depends on temperature and pressure, or volume and pressure, or volume and enthalpy. We just pick two. And for now, let's just speak temperature and volume. It means, according to the state postulate, that if we have temperature and volume, we can define anything, including the internal energy, which is what we're after here. So the state postulate says two properties. du is then, therefore, according to calculus, the change of energy with respect to temperature holding the volume constant times the change in temperature, plus the change in energy with respect to the volume keeping the temperature constant times the change of volume. This is how it reads. The full change in enthalpy and energy, which we're after, is the change in energy with respect to temperature by keeping the volume constant times the change in temperature, plus the change in energy with respect to volume by keeping the temperature constant times the change in volume. For convenience, we are going to define this quantity here, the u dt, keeping the volume constant, as CV. This is a name that we're going to give to this quantity right here. This is called the specific heat at constant volume. Every single gas has a different value of specific heat. Now, how do we read the specific heat? The specific heat at constant volume is the amount of energy necessary to raise the temperature of 1 kilogram of a gas by 1 degree when keeping the volume constant. So if you do an experiment and then you take that experiment and keep it at constant volume, you take air and put it in a rigid tank, for example, and you have exactly 1 kilogram of air and you measure the temperature, how much energy in the form of heat you need to put in to raise the temperature of that 1 kilogram of air by 1 degree Kelvin or 1 degree Celsius, which is the same, and that is the constant specific heat at constant volume is called. So then this definition of change in energy is equal to CV dt, CV being that specific heat at constant volume, plus this other quantity which we are going to deal with in a second. Now, if the fluid is an ideal gas, by definition, internal energy is not going to change as a function of temperature. It's not going to change if the temperature doesn't change, that is. If you don't change the temperature of an ideal gas, the internal energy of that ideal gas is not going to change. So internal energy is only a function of temperature. That's one of the characteristics of an ideal gas. Ideal gas is supposed to be a homogeneous chemical compound that doesn't change phase. So the only way to change the temperature is by changing the internal energy, and vice versa. The only way to change the internal energy is by changing the temperature, because there are two manifestations of the same thing. Internal energy is the molecular composition energy. It's the kinetic energy of the molecules, of the composition of the molecules. And temperature, microscopically, is exactly the same. So temperature and internal energy are two of the same things. One from the microscopic point of view, one from the macroscopic point of view, but they're two of the same. If you don't change the temperature, the internal energy cannot change, and vice versa. So for an ideal gas, that second quantity on the previous page goes away. For ideal gases only, this quantity goes away, because if you keep the temperature constant, the energy is not going to change. So it all comes down to this for ideal gases. This is it. For ideal gases, the change in internal energy is equal to the CV, which is that specific heat at constant volume. It's the constant that is tabulated, times the change in temperature. Every single gas has a different CV. Okay, that's it. The change in energy is equal to CV times the change in temperature. That's all we need. So for an ideal gas, internal energy is only a function of temperature. We said this here. Now, for finite changes of state, changes in internal energy may be determined by integrating that expression. So if we have du is equal to CV dt, this looks like a calculus relationship. Change in energy is equal to CV times change in temperature. Then we can actually calculate the change in energy by integrating this. So we can change, if du is equal to CV dt, then we can easily say that delta u, the change in energy from 1 to 2, from state 1 to state 2, is the integral from T1 to T2 of CV dt. Furthermore, this integration becomes very easy if we assume CV to be a constant. Now, if CV is a constant, it happens that if the specific heat for at constant volume for air is a number, or the specific heat at constant volume for CO2 is another number, they're going to be different for different gases. But if we can assume it to be a constant between the temperatures of T1 and T2, between state 1 and state 2, we can assume that CV behaves as an average value between T1 and T2. then that change in energy is equal to CV times the change in temperature. That's it. Delta U is equal to CV times delta T. Very simple. Now we have another relationship for another property, another thermodynamic property. We have the energy related to the temperature, this easy. We don't need tables, okay? Now we don't need tables for pressure, temperature, and volume because we have the equation of state, and we don't need temperatures for the energy because we have this constitutive relationship between energy and temperature. It's very simple. All we need to do is find out what the CV for that gas that we're using is. For air is one value, for CO2 is one value, for nitrogen is one value, depending on the system, depending on what the system is composed of. So now, change in energy is equal to CV times change in temperature. Remember that this only applies to ideal gases. Only to ideal gases. Alright, now let's deal with enthalpy now. Enthalpy is another thermodynamic property. It's another important thermodynamic property, and we're going to deal with enthalpy because we know we need it for certain processes. We know that the enthalpy is related to the heat in certain processes. Alright, so now let's deal with enthalpy the same way we dealt with energy. In this case, according to the state postulate, again, we're going to define enthalpy as a function of two properties, T and P. So we're going to say enthalpy is a function of T and P, temperature and pressure, as opposed to temperature and volume. We're going to say temperature and pressure now for enthalpy. And we're going to use the same chain rule from calculus and say dH, the change in enthalpy, is the partial change in enthalpy with respect to temperature at constant pressure times the change in temperature, plus the partial change of enthalpy with respect to pressure when keeping the temperature constant times the change in pressure. And for convenience, this quantity here, dH dt, at constant pressure, we're going to define as Cp, another constant. Now this one is called specific heat at constant pressure. Now we have Cv, which is specific heat at constant volume, and now we have Cp, which is specific heat at constant pressure. Okay? It's just for convenience of definition. Okay? Now what does this mean? Is the amount of energy in the form of heat necessary to raise the temperature of a gas, of a specific gas, of 1 kilogram of that gas by 1 degree when keeping the pressure constant. Okay? Not the volume now, the pressure constant. So imagine an experiment. You put 1 kilogram of air inside a piston cylinder assembly where the pressure remains constant as you add heat, because the piston is going to go up and the pressure inside is going to be kept the same. Instead of rigid, now it is a flexible one, but it's a flexible in the sense that the pressure remains constant. Then you add heat to that 1 kilogram of air and you measure the temperature. And you measure the amount of heat, the amount of energy in the form of heat that was necessary to raise the temperature by 1 degree, and that is that specific heat at constant pressure, that quantity, which differs from Cv. So the end result is that dH, the change in enthalpy, is Cp times the change in temperature plus dH dP times dP. What do we do with this second part here? Now for an ideal gas, the change in enthalpy as a function of pressure when keeping the temperature constant is equal to 0. And we can make an argument for that, but trust me, we can demonstrate this very easily. At constant temperature, you cannot change the enthalpy. Enthalpy is only a function of temperature, because remember that the enthalpy, that's only for an ideal gas. That argument is only true for an ideal gas. Energy is only a function of temperature, and enthalpy is only a function of temperature only, but only for ideal gases. So we end up that for an ideal gas, the change in enthalpy is equal to Cp dt. Change in energy is equal to Cv dt. The change in enthalpy is equal to Cp dt. That means that if we find Cp, we can find the enthalpy change very easily. So we've come up with a very simple constitutive relationship for the enthalpy. For an ideal gas, enthalpy is only a function of temperature. You don't need to know the pressure, you don't need to know the volume. The only thing you need to know is the temperature to know the enthalpy of a gas. Well, you need to know the constant Cp, but it only changes as a function. The enthalpy only changes as a function of temperature. Okay. Now later on we're going to show very simple equations that demonstrate why enthalpy is only a function of temperature. Well, you can see it from here, but why is it that we cancel this quantity from the previous equation? Why is it that we cancel these? Why is it that we are saying that at constant temperature enthalpy cannot change and therefore this quantity goes to 0? And leading to this relationship here. Now furthermore, for finite changes of state, likewise we did for the energy, changes in enthalpy may be determined by integrating this expression. So if you have dH equals Cp dt, we can do this in a finite change of state. Change of enthalpy between state 1 and state 2 is the integral from T1 to T2 of Cp dt. All we're doing is taking the derivative to the other side. So the change in enthalpy is equal to the integral Cp dt. Don't worry, we are not going to have to solve any of these integrals. All we're coming up with are algebraic relationships. Very simple algebraic relationships. Now this integration is very easy if Cp can be assumed to be a constant within this range of temperatures. If we can say that between T1 and T2 of this particular process, Cp remains a constant, whether this is air or CO2 or nitrogen or oxygen, let's assume that Cp remains constant in that range. We know it's going to be different for air and for nitrogen and for oxygen and so on, but let's just focus now on the specific process for a specific gas. And let's say that within that range of temperature, Cp is a constant. So now the change in enthalpy is Cp times T2 minus T1. Very simple. Another constitutive relationship for another property. So now we have pressure, temperature, and volume related together through the state equation. Very easy. P times V is equal to RT. Very simple. All we need to know is R for that specific gas. And now we have energy. The change in energy is Cv times the change in temperature. And now we have enthalpy. The change in enthalpy is Cp times the change in temperature. By the way, these energy and enthalpy relationships are only true for ideal gases as long as you can say that Cv and Cp are constants. Okay? Furthermore, let's see the relationship of Cp and Cv. Now remember the definition of enthalpy. This is definition. H is equal to the energy plus PV plus pressure times specific volume. Enthalpy is equal to energy plus PV. That is the definition of enthalpy. Okay? Nothing more than that. It doesn't matter how we interpret it. It's just two forms of energy combined. Internal molecular energy plus this form of, you can argue it's some form of mechanical energy, PV. Enthalpy is U plus PV. And remember also that PV, for an ideal gas, according to the equation of state, is equal to RT. Now let's plug this RT back into the definition of enthalpy, and we say H is equal to U plus RT. And now let's take a derivative. dH is equal to du plus R times dt. Well, the derivative doesn't affect R because R is a constant. It's called the ideal gas constant. It's called a constant for a reason. So that derivative that we are trying to apply doesn't affect the R. Again, don't worry, we are not going to be solving differential equations in this class. I'm only doing this for the sake of demonstration, for the sake of formulation. dH is equal to du plus R dt. Now we found that dH is equal to Cp dt. We did that on the previous formulation. We found that du is equal to Cv dt. So let's plug that in back into the definition. dH is equal to Cp dt. du is equal to Cv dt plus R dt from the definition. So now we have dt, dt, and dt, and those cancel out. We can take that as a common factor and cancel those out. And what we're left with is that Cp is equal to Cv plus R. Okay, so Cp is always greater than Cv. That means that you need more energy to change the temperature of a gas when it's kept at constant pressure than what you need energy when the gas is kept at constant volume. Okay, remember that Cp is a specific heat at constant pressure, Cv is a specific heat at constant volume. How much energy do you need to raise the temperature of 1 kilogram of a gas by 1 degree when it's kept at constant pressure? And the other one is how much energy do you need to raise the temperature of 1 kilogram of gas by 1 degree when it's kept at constant volume. Now these two are offset by R. R is a gas constant. So if R is a constant, we know that R is a constant for the gas, then Cp and Cv must be constants because they are only differentiated by R. Well, it turns out that they're not quite yet constants. They're not quite constant. They actually change a little bit with temperature, but the difference between them, Cp minus Cv, is always R. And that's it. So also let's look at this parameter K. The parameter K is the ratio of the specific heats. We just defined the difference between Cp and Cv as the gas constant R. We just found out that the difference between Cp and Cv is the constant R, is the gas constant. Cp is equal to Cv plus R. It is also convenient to define another quantity called K as the ratio of the specific heats. Remember that Cp, according to this, is always larger than Cv, because Cp is equal to Cv plus R. It is always larger. So we can define another parameter called K as Cp divided by Cv, and that parameter is always going to be larger than 1. Always, because Cp is larger than Cv. And we call this the ratio of specific heats, or the isentropic constant. You can call K the ratio of specific heats, or just simply the isentropic constant. Why do we call it the isentropic constant? Because it turns out that when an ideal gas undergoes a reversible adiabatic process, a process where there's no heat addition or release, an insulated system, thermally insulated system, there's no heat addition or subtraction, and it's a reversible process, that means that we can, with the same effort, we can go back to the original state. This process will follow a process line where PV to the K is equal to a constant. It looks like a polytropic process, the ones that we defined before, but where the power n is specifically the ratio of specific heats. If the power n of a polytropic process is equal to the ratio of specific heats for that gas, then we call this an isentropic process instead of a polytropic process. It's a process where entropy doesn't change, but we don't know what entropy is yet. Let's just keep this as a definition. In this kind of polytropic process, in this case isentropic process, adiabatic reversible means isentropic. P1 times V1 to the K is equal to P2 times V2 to the K. The relationship or the product P times V to the K remains constant throughout the process. Okay, now let's look at these tables for Cp and Cv, and this table is provided to you in the online, in Florida Online. Let's look at this table. This table says that for the 6 gases under consideration, air, nitrogen, oxygen, CO2, CO, and hydrogen, we have Cp, we have Cv, and we have K, the ratio of the two. Now notice that Cp and Cv actually change a little bit with temperature. They change by about 10% as we raise the temperature. They actually grow with temperature, but the difference between the two is always the same, because the difference between the two is R. Notice that for nitrogen, these quantities are about the same as for air, because air is mostly nitrogen. Now for oxygen, these quantities are quite different. Obviously for hydrogen, they're quite different, because they're much higher, because the molecular weight of hydrogen is the smallest one of all. It's 2. So, and here they are. And in all cases, they actually change with temperature. They change with temperature by about 10%. But under certain conditions, we can assume them to be constant. If we have a process where the temperature changes, let's say from 400 Kelvin to 450 Kelvin, might as well assume that that value Cp and that value Cv is a constant. Let's assume that it's just 1.015 and 0.72 or 0.73 for Cv. Let's assume it's a constant, and then calculate the energy and the enthalpy with these quantities or these equations that we just derived. Okay, so this is the table of specific heats, which is provided to you in Florida Online. All right, now from the table before, we noticed that Cv and Cp are not quite constants. They change by about 10% between 300 Kelvin and 1000 Kelvin. So if you have a process that raises the temperature that much, then saying that they're constant is not a good assumption. It's probably an approximation that's not going to yield very accurate results. So we can actually consider them to be variable, and variable means they are functions of temperature only, Cv and Cp. Now we cannot say that the change in energy is Cv times delta T, and the change in entropy is Cp times delta T. Okay, we have to stick to the original formulation, the original integral. Now, at best, this adds additional complexity to the process. If we are going to need these properties frequently, it is more convenient to perform the integration once and then tabulate the results. So somebody already tabulated the results, tabulated the values of energy and enthalpy for all the gases for us as a function of temperature. Somebody already did these integrations, assuming that Cp and Cv are not really constants, and did the tabulation for us. So if I tell you in a thermodynamic process you cannot assume Cv and Cp to be constant, then you have to rely on the tables to calculate energy and enthalpy. Not for pressure, volume, and temperature. For pressure, volume, and temperature, always use the equation of state. Remember, as long as you're dealing with an ideal gas. But for energy and enthalpy, You use the equations if you can assume that Cp and Cv are constant, but if not, then you have to rely on these tables. Now these tables contain values of energy and enthalpy. Remember that energy change is the integral of Cv dt, and enthalpy change is the integral of Cp dt. If you cannot assume Cv and Cp to be constant, then you have to conduct this integration. We don't want to do integrals in this class, so we go to tables. Okay? Now, these is tabulated with respect to some kind of reference temperature. The reference temperature is selected to be, in most cases, especially in the tables that I provided to you, 0 absolute. So the energy at 0 absolute temperature, 0 Kelvin, is 0, and the enthalpy at 0 absolute temperature, 0 Kelvin, is equal to 0. And thereon, the energy increases with temperature and the enthalpy increases with temperature. It's monotonic. Temperature increases, energy increases. Temperature increases, enthalpy increases. So then we can say, according to this representation, this is a tabulated representation, the change in energy is equal to the energy at temperature 2 minus the energy at temperature 1. So forget about that Cv delta T and forget about that Cp delta T for enthalpy. We rely on tables. So we go with the temperature to a table and find energy at state 2. We go with the temperature to a table and find the energy at state 1, at temperature 1. We subtract the 2, and now we have the change of energy. So if we need the change of energy to apply the first law of thermo, this is how we get it, from tables. So again, we use the tables if we cannot say, or I don't tell you, to assume that the specific heats are constant. If you can assume that the specific heats are constant, then you just use the simple equations for delta U and delta H. There we go. So we have now an equation for delta U, and for delta H, it's not really an equation, it's a way of actually getting those directly from tables. So the tables of ideal gas properties are developed on this basis, on the basis of using a reference temperature, and that's fine because then you can just log into the table with a temperature and extract an energy at any particular state. So here's a snapshot, for example, of the tables for air. There are tables for air, for CO2, for CO, for nitrogen, for oxygen, and for hydrogen. In the table of air, you go in at any time. Remember, this is only a function of temperature. You go in at a temperature and you extract the enthalpy, the energy, some value called C0, which we'll look at later. So we don't need C0, or I'm sorry, S0, which is called is a component of the entropy. It's not truly the entropy. PR and VR, these are quantities that we are going to be looking at later. Okay. So we go in with the temperature in Kelvin and we subtract the enthalpy, specific enthalpy, or the specific energy in kilojoules per kilogram. Okay, so we don't no longer use the Cp and the Cv. We go to the table with temperature and we extract H and U. This table is a snapshot. It has temperatures from 200 all the way to 740, 200 to 440, 450 all the way to 740. There's a second page to this table, actually a third page. It goes all the way to 3,000 and something degrees. Same it goes for CO2, for nitrogen, for oxygen, and so on and so forth. It's very simple. Unlike the tables for substances where you have to go in with two quantities, temperature and pressure, or temperature and volume. In this case, you just go in with temperature. So much nicer to deal with ideal gases. It's so much easier because they do not change phase, or they're not bound to change phase within the normal range of temperatures of thermodynamic processes. Alright, so now let's look at some of these processes in the PV diagram. Okay, we know that the PV diagram is very important because it determines the work. Area under the curve of the PV diagram is the work. And that's true for substances, that's true for gases. It just happens that for gases, we don't worry about the saturation dome. It doesn't exist. It's very, very far away to the left. It's so far away to the left that we don't even draw it. Okay? Isometric processes are vertical lines in the PV diagram. Obviously, if the volume doesn't change, we go from state 1 to state 2 in a vertical line, either up or down if we're increasing the pressure or decreasing the pressure. Obviously, higher volumes are vertical lines on the right side. So an isometric process, a process in which the volume doesn't change, is a vertical line on the PV diagram. Well, we know that. Let's look at an isobaric process. An isobaric process, remember, is a process where pressure doesn't change. Pressure remains a constant. Let's look at the work. If the pressure remains the same, then the area under the curve is just the pressure times the change of volume. It's the area of a rectangle. It's very simple because that integral of P dV, the pressure comes out, and it's P times the change of volume. That's what the work is. Pressure times the change of volume. Very easy. Okay. Now, if we go back to the formulation, the first law of thermal, remember the first law of thermal says that change of energy is equal to heat minus work, or basically heat is equal to change of energy plus work. Change of energy is U2 minus U1, and work is equal to pressure times the change of volume. This is only for isobaric processes. Change of heat is then, therefore, if we rearrange this, U2 plus P2 V2 minus U1 plus P1 V1. By definition, this is the enthalpy at state 2, and this is the enthalpy at state 1. This is just a matter of definition. So in isobaric processes, the heat transfer is equal to the change of enthalpy. That's why the enthalpy is important. It's a quantity that is important because we can calculate the heat by knowing the change of enthalpy if the process is isobaric, only for isobaric processes. Okay? So isobaric processes are represented in the PV diagram as horizontal lines, obviously, because in a PV diagram the pressure goes on the y-axis, and if the pressure doesn't change from state 1 to state 2, that is a horizontal line. Higher pressure will be a horizontal line above the other one. So this is an isobaric process. This is another isobaric process. It can go from left to right or from right to left, depending on whether you're increasing the volume or decreasing the volume. Let's look at an isothermal process. Remember, an isothermal process is a process where the temperature doesn't change. So if you're confronted with a process in which the temperature doesn't change, in the case of an ideal gas, remember that pressure volume is equal to RT. Pressure times volume is equal to RT. Pressure volume is equal to a constant. If the temperature doesn't change, then that entire right hand side becomes a constant. That means that P1 V1 is equal to P2 V2. Alright? Now, if the pressure doesn't change, if the temperature doesn't change, let's look at the work. Work from 1 to 2, which is equal to P dV, the integral of P dV. The pressure is equal to a constant divided by a volume, which is RT divided by a volume. Because RT doesn't change, you can take it out of the integral. So it's dV over V. The integral of that is the log of V2 over V1. So the work from 1 to 2 is equal to R, the gas constant, times the temperature, times the log of V2 over V1. But according to this relationship, V2 over V1 is equal to P1 over P2. So you can pretty much say that this is equal to RT times the log of P1 over P2. Okay. So if the volume increases, the log of a number larger than 1 is positive. The log of a number less than 1 is negative. So here you go. That respects the sign convention. If the volume increases, you have positive work. If the volume decreases, you have negative work, directly out of this logarithm. So this is an isothermal process. It responds to a relationship where PV is equal to a constant, directly out of the equation of state. PV is equal to a constant. It means that P is equal to constant divided by volume. So in a PV diagram, an isothermal process will look like this. It looks like an asymptotic line. P is equal to a constant divided by V. This line stretches all the way to infinity here, and it stretches all the way to infinity on the right hand side. A larger temperature, that's a PV equals to a constant line, or basically P is equal to a constant divided by V. A larger temperature will be a line kind of parallel to that one, but higher than it. So this is an isothermal process with a slightly larger temperature. Now let's look at an isentropic process. An isentropic process, as we defined it a few slides ago, is a process in which there is no heat transfer. It's an adiabatic process that occurs reversibly. Reversibly means with the same effort, you can actually go back to the original state. An adiabatic reversible process is also known as an isentropic process. And we already defined that an isentropic process will follow the curve P times V to the power of K equals to a constant, where that K is the ratio of specific heat, Cp over Cv. In that case, we know that P1 V1 to the power of K is equal to P2 V2 to the power of K. This belongs to the family of polytropic processes, and we know that polytropic processes, this integral of PdV reduces to P2V2 minus P1V1 divided by 1 over K, where K is the exponent of the polytropic expression, or the power of the polytropic expression. So we already did this word calculation a long time ago. We don't have to solve that integral. If we're given a polytropic process, specifically if we're given an isentropic process in which the exponent is equal to the ratio of specific heats, we know that the work can be calculated as P2V2 minus P1V1, 1 minus K. That's it. Now, how would these particular expression look in a PV diagram? We know we can see P is equal to a constant divided by V over K, or V to the power K. Now, as opposed to the isothermal process, where it was just P equals to a constant divided by V, now we have a slightly larger denominator. When we send this V to the K to the denominator here of the constant, that's slightly larger, because K, we know, is always larger than 1. K is the ratio of specific heats, Cp over Cv. Cp is always larger than Cv, therefore this K is always larger than 1. And therefore, in a PV diagram, these isentropic processes will look almost like an isothermal process, but a little steeper. This is the equation of PV to the K equals to a constant. And that's it. That's all we want to know about all the different types of processes in a PV diagram for ideal gases. Remember, in ideal gases, in the PV diagram, we don't have to worry about the saturation dome. Don't worry about the saturation dome, because it's very little and far away to the left that we don't even consider. An ideal gas is a substance that is very, very far away enough from the saturation dome that these relationships between pressure, temperature, and volume are very easy to handle with this very simple equation that's called the equation of state of an ideal gas. So this is the introduction to ideal gases. In the next lecture, we're going to be actually solving problems of ideal gases. We're going to be solving one big problem of an ideal gas. And then we're going to do some reviews for what's coming up in the assignments and the test and so on. So thank you for your attention, and I'll see you next class.